Let's add up the terms in a geometric progression in general. Pick a value for r. Here's the series I want to evaluate.
The sum, k goes from 0 to infinity, of some number r raised to the kth power.
These series have a name.
These things are called geometric series.
We've already seen this when r equals 1/2.
Right, so if I plug in r equals 1/2, and look at this geometric series, this series we've already evaluated. It converges, and its value is 2.
For certain other values of r, we can also figure out what's happening with this series right away.
Instead of considering 1/2, let's think back to this original geometric series, and let's plug in 1 for r. If I plug in 1 for r, does this geometric series converge or diverge? Well, it's not too hard to think about. Let's start writing down what this series looks like. This series would be the 0th term would be 1 to the 0, which is 1. The k equals 1 term would be 1 to the 1, which is 1. The k equals 2 term is 1 squared, which is 1. Right? This series is just 1 plus 1 plus 1 plus 1, and so on. Does this series converge or diverge? This series diverges, because the limit of the partial sums is infinity.
Something bad also happens when r equals -1.
So yeah, instead of looking at r equals 1, let's plug in r equals -1 and see what sort of terrible thing happens. So if r equals -1, well, then I can start writing down the first few terms of this series as well. When I plug in k equals 0, I get -1 to the 0th power, which is 1. When I plug in k equals 1, I get -1 to the 1st power, which is -1. Then I plug in k equals 2, and I get -1 squared, which is +1. Then I plug in k equals 3, and I get -1 cubed, which is -1. So what this series looks like is 1, -1, +1, -1, +1, -1, +1, -1, and so on. Does this series converge or diverge? More precisely, what's the limit of the partial sums? Well, when I add just the first term, I get 1. When I add the first 2 terms, I get 0. When I add the first 3 terms together, I get 1. When I add the first 4 terms together, I get 0. And this pattern continues. When I add the first 5 terms together, I get 1. When I add the first 6 terms together, I get 0. The partial sums are flip-flopping between 1 and 0. And does a sequence 1, 0, 1, 0, 1, 0, does that sequence converge? No. And because the sequence of partial sums doesn't converge, the original series doesn't converge either.
Let's think about what happens for some other values of r. Remember, to evaluate a series, I want to take a limit of the sequence of partial sums.
And symbols. Here's the partial sum. S sub n is the nth partial sum of this geometric series, and it's the sum of the terms from k equals 0 all the way up to n. So here's the k equals 0 term, here's the k equals 1 term, dot, 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 hides all the other terms, and then here's the k equals n term. And the real question is, what's the limit of these partial sums? And if I take the limit of this as n goes to infinity, that's the value of this series.
I want to compute the limit of that sequence.
So I really want to compute the limit of this, the nth partial sum. And if I can compute this limit, then I've computed the value of the geometric series. Well, I've been calling this nth partial sum S sub n. So to compute the limit of S sub n, first thing to do is to get a better handle on S sub n. And the trick for doing that is to multiply S sub n by 1 minus r. Well, what's that equal to? Well, that's 1 minus r times, here's an expression for S sub n, right? The nth partial sum is just the sum of the terms k from 0 up to k equals n. But now I can distribute. So here I've just written down 1 minus r times that quantity. I haven't changed anything. But by distributing, I can rewrite this as 1 times S sub n minus r times S sub n. And now I can do a little bit more manipulation here. Subtracting r times this is the same as subtracting this. I can multiply each of the terms by r. But now each of these terms also can be rewritten. R times r to the 0 is r to the first. R times r to the first is r squared, and so on until I get to r times r to the n, which is really r to the n plus 1. So instead of writing it this way, I could rewrite r times s sub n as minus r to the first plus r squared until I get to r to the n plus 1. But now a wonderful thing happens. Lots of these terms cancel terms up here. Well, how so? R to the 0 survives, but r to the first is killed by this subtract r to the first here. Inside the dot 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 there's an r squared, and that's killed by this r squared term. And so on. All of the terms up here, except for r to the 0, all of these terms are killed by something down here. But then I've also got this extra r to the n plus 1 term that doesn't have anything up here to kill. So what's this equal to? Well, this ends up being equal to r to the 0, which survives. All of the middle stuff dies. And then this last r to the n plus 1 term survives, and I've written it down here. But r to the 0 can be written as just 1. So I could rewrite this as 1 minus r to the n plus 1. All of this is to say that 1 minus r times this nth partial sum is 1 minus r to the n plus 1.
Let's divide by 1 minus r.
Okay, so we've got 1 minus r times s sub n is 1 minus r to the n plus 1. And assuming that r is not 1, well, then I can divide both sides by 1 minus r, and I get that 1 minus r times s sub n over 1 minus r is equal to 1 minus r to the n plus 1 over 1 minus r. Now I can cancel the 1 minus r's, and I've got a formula for the nth partial sum. The nth partial sum is 1 minus r to the n plus 1 over 1 minus r.
Now I'll take the limit.
So the limit of s sub n, well, here's a formula for s sub n. So the limit of s sub n is just the limit as n goes to infinity of 1 minus r to the n plus 1 over 1 minus r. That's the limit we have to calculate.
When does that limit exist?
We can compute this limit using our limit laws. This is a limit of a quotient, so it's the quotient of the limits. Limit of the denominator is the limit of a constant, and limit of a numerator is the limit of a difference, which is the difference of the limits. All that is to say that using the limit laws, this ends up being 1 minus the limit as n approaches infinity of r to the n plus 1 over 1 minus r. Now, how do I calculate this limit? What's the limit of r to the n plus 1 as n approaches infinity? Well, the situation is that if r is bigger than 1 or r is less than minus 1, then the limit of r to the n plus 1 as n approaches infinity isn't a finite number. And consequently, when this happens, when r is bigger than 1 or less than minus 1, then the limit of the partial sums diverges, and consequently, the original geometric series diverges.
But if r is between minus 1 and 1, then we're good.
Well, exactly. In that case, if r is between minus 1 and 1, then the limit of r to the n plus 1 as n approaches infinity is equal to 0. If I take a number between minus 1 and 1 and raise it to an enormous power, that number gets very close to 0. Well, this then lets me calculate this. If I want to calculate the limit of 1 minus r to the n plus 1 over 1 minus r, that then is 1 over 1 minus r, because the limit of r to the n plus 1 is 0.
Let's summarize the situation for geometric series.
So the geometric series, the sum k goes from 0 to infinity of r to the k, is equal to 1 over 1 minus r if r is between minus 1 and 1. And we know that because we calculated the limit of the partial sums to be 1 over 1 minus r. In the case where r equals 1 or r equals minus 1, we already saw it diverged. And if r is bigger than 1 or r is less than minus 1, then it also diverges. So this actually covers all of the cases.